the unit map on the inside. So this is just a way of saying that I have two maps up from uz tilde to uz tilde squared. And I didn't tech it because it starts to look a little cluttered, but the co-unit of that adjunction would take zu to the identity. So that gives me a map back down. And that's looking good. This is like the start of a cosimplicial diagram, and in fact it is. So from this, I get 3 maps upwards. So I get 3 maps up to uz tilde cubed. And again, I didn't draw them in, but the co-unit maps give us 2 maps back down. And they satisfy the cosimplicial identities. So in this way, we build this cosimplicial gadget. So this whole thing here lives in delta-shaped spaces. So delta-shaped diagrams in spaces. So now remember, we're trying to build this thing that sees the homology of X, and I fattened up my construction, and so now I'm just going to glue it all together in some homotopy meaningful way. So the Z completion of a space we define as all of this stuff glued together. So that's taking the homotopy limit over this delta category, and this thing in red, I'm just going to shorthand the note as this. So the dot is supposed to help us remember that it's cosimplicial.
Niko?
Yes.
Is this the same as just doing the plus construction to like the derived subgroup of the fundamental group of X? I think that's like a stable equivalence.
I'm not sure.
Okay.
So the plus construction is supposed to make pi1 nilpotent, right?
So I think my understanding is that if you have like a perfect, maybe it needs to be, sorry. I was just thinking maybe doing the plus construction would make the fundamental group abelian, and so like maybe be isomorphic to the homology. And so,
yeah. So in general, you can, this for nilpotent spaces, this won't change pi1. So
okay.
I guess, so yeah. I guess the honest answer is I'm not sure. If you're nilpotent, it won't, yeah.
Okay, so it doesn't like abelianize pi1.
Correct.
Oh, okay, okay.
Yeah.
Thanks.
Yeah. Yeah, so I glue all this stuff together and I get the homotopy limit. And this eta map here gives me a natural comparison map from X to the completion. And now, since we've been staring at Zoom probably more than we'd like to over the last few weeks, here's a little de-stressor. This is Rumi. He's here to lower everyone's heart rate. And it's a natural opportunity if there are any other questions about anything we've talked about so far. Awesome. Okay.
What's the name of the puppy?
Rumi, like the poet.
Sorry? Oh, yes.
Yeah. He's cute. Thank you for asking. So back to the math. The upshot of all this is that I have this cosimplicial diagram. It's co-augmented, so I have this map here, co-augmented into the cosimplicial thing. I'm defining the Z completion as just all that stuff glued together. Think of that, that's really what the homotopy limit is doing for us. And remember, we started this journey wanting the following two things. And it's not crazy difficult to check that we do still have this first one. That's good. The second one, we certainly have a better chance at, but a priori, it's not clear if we always get this. And just to sort of hint at where we're going, often we actually sort of exceed what we were looking for. This map here, X to the completion, is actually often a weak equivalence. And when exactly that happens and how that happens is sort of where we're headed. So I just keep that in mind. So that's the classical story. That's spaces and ordinary homology and completion with respect to ordinary homology. So what I want to do now is outline or just sort of give a brief intro to the setting where I work, which is in algebras over an operad in symmetric spectra. If you haven't heard of any of those words, that's, again, totally fine. We're going to give a sort of a brief introduction here. But the cool thing is that sort of once we've arrived there, there's a lot of really nice analogies between classical story and this new setting.
Niko, one small question.
Yeah.
Are you kind of using well, you haven't used the word, but are you kind of using localization and completion like interchangeably here, or is this?
Great question. Yeah. So this is really what you always get from localization. Like those are the universal properties of localization. Yeah. And so the question, this is sort of implicitly asking the question, when does the completion provide a localization?
Okay.
Because the answer is not always.
Okay.
So
yeah. Yeah. Go ahead. Sorry.
Localization, like if you do like a left Bousfield localization, it's this really big construction. It's like a small object argument kind of thing. You're gluing on infinitely many cells, infinitely many times. So to actually get a handle on what it is can often be pretty difficult. So it's nice to know when this, I mean, this is still an infinite construction, but it's much, much smaller. And there's a spectral sequence, and it's just, you can get your hands on it easier. So it's sort of implicitly asking, when can I use this concrete completion construction as a localization?
Thanks.
Yeah.
Sorry, I have a question as well.
Yeah.
In line of ideas, is the problem with localization also that maybe it's not an accessible localization? Like, is it clear that the left Bousfield localization exists in this case?
Right. So that's a question you have to ask. Bousfield does prove that localizations with respect to homology exist, but it's certainly not a trivial thing to prove.
Okay.
And certainly in other contexts, whether or not you can do a left Bousfield localization is not always clear. But this construction you can always at least do, right? I can't always define the completion. So, yeah.
Okay, thanks.
Mm-hmm. Any other questions? Cool. So, right, so I want to get into now the setting where I work, and that begins with, I have to tell you what an operad is. So you can define this in any symmetric monoidal category. So just a category with a nice way to multiply the objects. Concrete examples are great to keep in mind. So for instance, I could consider spaces and the Cartesian product. Right, I can take two spaces and form a product. That's all we're saying here. If I want to do that in a pointed context, I'd have pointed spaces and the smash product instead of the Cartesian. Or for a more algebraically flavored thing, you consider just abelian groups with ordinary tensor products. So this is really tensor over Z. If you're not familiar with operads, I want to offer the following definition, which should maybe be in scare quotes. But the idea is that an operad is just a sequence of objects. So each of these OIs is an object in my category. And the reason, one of the reasons we're interested in operad is because what they can do is encode algebraic structure. So think of it, again, if you're not familiar with operads, think of it as sort of a black box that is encoding algebraic structure in your category. And what I mean by that is that we sort of care about the operad because of its algebras. And the algebras over an operad are exactly those objects with extra algebraic structure defined by the operad O. So a good analogy to keep in mind is that algebras over an operad are a lot like modules over a ring. And again, I think this is best to understand through example. So if I pick different symmetric monoidal categories and I pick different operads, we can construct the following. So if I imagine us living in abelian groups and my product is the tensor product, if I choose my operad right, then the algebras can be precisely those abelian groups with an associative multiplication an associative self-multiplication. And those are exactly rings. So in this way, right, the operad is picking out those objects of the category, namely those abelian groups, that have the additional structure of being rings, not just abelian groups. For a more topologically, topological example, consider spaces in the Cartesian product. In a similar way, I can pick an operad such that the algebras are spaces with an associative self-multiplication. And if you want to sort of beef this up, these could be eventually A infinity spaces. Or if you choose what's called the little disks operad, which is one of the first uses really, then the algebras can be exactly infinite loop spaces. So this was the original motivation of Peter May's geometry of iterated loop spaces. Cool. So our basic setting where we work is considering algebras over an operad in symmetric spectra. For technical reasons, I want to assume my operad is reduced, which just means the zeroth object is trivial. And again, if you're not familiar with spectra or symmetric spectra, just replace symmetric spectra with space and the same kind of idea. All the same story works. So the big thing to keep in mind as we move forward is just the setting that we're in is algo. And all that is symmetric spectra with extra algebraic structure encoded by O. And the only assumptions we're making on the operad is that it's reduced. So this is really any algebraic structure you want that can be encoded by an operad. So A infinity, E infinity, En, anything like that is included. So in particular, like commutative ring spectra, associative ring spectra are all sort of covered by this context. So as you may be thinking, operads can be pretty complicated, right? It's this infinite sequence of objects, and if I were to have written out all of the axioms that define an operad, it would probably take 2 or 3 slides. Like it's kind of rough. So to make our life easier, we're just going to filter it. Right? That's usually a good way to get a handle on more complicated things. How does this filtration work? Well, given an operad O, I'm going to define a bunch of new operads, but they're built out of O. So I'm going to define this operad tau1 of O, and this is going to be a much simpler gadget because it agrees with O at level 0 and agrees with O at level 1, but then I've killed everything higher. Okay, so from level 2 and on, I've mapped everything to a point. So this has thrown away quite a bit of information. But the advantage is that it's sort of simpler to understand. And then I can also throw away a little bit less information. I can build this operad tau2 that agrees with O at levels 0, 1, and 2, and then I kill everything off. And we can similarly define tau3, and we can keep going.
Can I ask you a question about that?
Yeah.
How are you going to define the composition if you kill off the things in higher arities? Do you just define it all to be like the same thing, or?
Yes. So the operad structure is canonically induced by O. It's the same composition maps.
Right, so like, is this like a quotient of O, or is it a something of O? Because if you're sort of just making all the higher arity operations be the same, then it looks like it's a quotient of O.
So it's not a quotient as far as I know, but there is a map. We'll talk about this in a second. There is a map from O to each of these guys. Okay. That you get just by truncating. So for instance, this O of 2. Let me kill this for now. Actually, O of 2. Right. I can map this down to a point. So that gives me a map of symmetric sequences.
Yeah. Okay.
And then you can check.
What I meant. This is sort of what I meant when I was thinking about quotients. Okay.
Yeah, so it's just, you just map everything to a point and then you check that there is still an operad structure.
Okay, thank you.
Mm-hmm. Thanks for asking. Any other questions? Cool, okay. So yeah, so that's a great question because that points out there's a relationship between these new operads. So if I map O of 2 to a point here, like I've done, that'll induce a map of operads, tau 2 of O to tau 1 of O. And in the same way, I can map O of 3 to a point, and that'll induce a map tau 3 to tau 2. And so on and so forth. So, yes, and a good way to just sort of mantra to keep in the back of your head, tau k just kills structure. It kills structure above level k. And from all this, we get a bunch of maps of operads. So I have my tau 1, I have my tau 2, my tau 3, and ad infinitum. I have these maps that I talked about on the previous slide. And then as Roy and I were talking about, sort of, there's a map from O, from my original operad, to all of these guys. So there's a map of O to tau 1 of O that I get just by mapping all of those higher levels to a point, and similarly to tau 2 and tau 3, and so on. Now, a little bit ago, I said that a good analogy is that algebras over an operad are like modules over a ring. And if you have a map of rings, that always induces a change of rings adjunction, on the corresponding module categories. And in the same way, I mean, really the same way, any map of operads gives you a change of operads adjunction. So if I look at this bottom layer, this map of operads, O to T1 of O, gives me a change of operads adjunction on the corresponding algebra categories. So there it is. This.
Can I ask a quick question?
Yeah.
So this, I mean, this seems like some kind of Postnikov tower construction.
Yes.
Are there some like convergence type results that allow you to approximate O from this tower? And similarly, can you sort of recover O algebras from sort of the cosimplicial diagram of algebra categories that you get by taking a limit over that thing?
Yeah, that's it.
In that direction.
That's a great question. So if you're just looking at symmetric sequences, this tower will always recover O. A very interesting question to ask, which is related to everything we're doing. So how this adjunction actually works is if I take an X in here, it goes to tau 1 of O, and then there's a circle over construction X. So this is kind of like if I had a map of rings R to S, if I do mod R, mod S, something in here goes to, let's see, like S tensor over Rx. So same thing here. So out of this tower, you can construct, if I actually like plug in an object, I can get like tau 1 O circle over O of X, tau 2 O circle over O of X, and so on. And then you can ask, does this recover, can I get X back from this? And it turns out that this tower is exactly the Goodwillie tower of the identity functor on AlGo.
Oh, okay, interesting.
So then you do have all those interesting convergence questions, and it turns out for zero connected guys, it will converge. And you can check that the identity functor on AlGo is zero analytic, because there's a Blakers-Mancy theorem. So yeah, thank you. That's a great question. Hopefully that answers. Cool. But yeah, so for today, I'm really just interested in this bottom level map here, and apparently can't draw circles. But it's from this adjunction here that I'm going to define my invariant. So from this adjunction from the bottom level, I'm going to define an invariant on AlGo. And that's what we call the TQ homology, so the topological Quillen homology. So the TQ homology of an algebra A is just what I get when I take something in here, I go to QA, and I come back to UQA. And then the TQ homology groups are just the homotopy groups of that gadget. What has this bought us? Well, AlGo as a category is not great. It's not stable. It's not left proper. It's not tremendously fun to work in. But AlG over tau 1 of O is actually isomorphic to a module category, and so it is stable, and it does have a lot of really nice properties. So what we've done here is we've taken an O algebra, which is pretty complicated, and sort of canonically factored it through a stable category and come back. So we've certainly thrown away some information, but it also has become easier to work with. And as I mentioned, if this, if operads are new to you, the really cool, I mean, even if not, the really cool thing is that there are a lot of really strong analogies between algebras over an operad, TQ homology, and spaces ordinary homology. So the big thing to keep in mind is that, okay, Z homology, so just homology with integer coefficients, and spaces is like TQ homology and O algebras. To make this a little more precise, we'll fill out a little table here. So the sort of most, maybe the first analogy you think of is the construction. So one way to construct homology was to consider this adjunction between simplicial sets and simplicial abelian groups. And we have a similar kind of thing going on with O algebras. And the ordinary homology of a space can be defined as, I mean, this is a natural isomorphism, so it can be defined as the homotopy groups of this UZ tilde thing. And that's exactly how I define TQ homology groups of an O algebra. A nice theorem that we've all learned is the Reminisce theorem, which tells us, relates homotopy to homology. And one way of phrasing the connectivity statements there is precisely the connectivity of this unit map in spaces. And there is a similar TQ Reminisce theorem. The estimate's a little better, so that's cool, but same sort of idea. And just like there's a Whitehead theorem for spaces, there's also a TQ Whitehead theorem. And these last two results are due to Harper and Hess, 2015. So with that analogy in mind, in the same way that we built completion with respect to integer homology, I can ask for the part of an O algebra that TQ homology sees, and see if I can recover that via completion. So one way to do this would be to start with this junction, comes with a unit map, and then I just iterate this unit map. So I have A into UQA, and then I just fill out the rest of this cosimplicial diagram. And in this way, I will define the TQ completion of an O algebra as, again, just what I get by gluing together this cosimplicial diagram. So that's how I'll define TQ completion.
Hey, Niko, can I ask another question?
Yes.
So, so this works for any symmetric monoidal category. We can sort of make this, or we're specifically working with a symmetric spectra, right?
So an operads, work in any symmetric monoidal category. Right. For this to work, I suspect you could do another context, but I'm really looking at symmetric spectra or one level of generality higher modules over any commutative ring spectrum. So
right. So I guess my question is, what if I plug in a certain operad? Am I going to recover like sort of topological André-Quillin homology in the sense of like, say, McCarthy-Manassian, for example, or maybe other examples of classical André-Quillin homology can be recovered if I plug in a different symmetric monoidal category and do this construction? Yeah,
that's a great question. And the answer is I'm not sure. That's something I want to explore in the future. In particular, like the topological André-Quillin homology defined by Bastera and Bastera-Mendel that's used in like Peirce-Hawkins obstruction theory. It'd be really cool if this recovered that. And in some sense, they're morally similar because TAQ can be defined as like a derived in decomposables, and they just define that for commutative ring spectra. This is kind of the same thing. You're killing off the higher algebraic structure. But the answer is I'm not sure.
Right. Yeah. I guess I'm a little confused about the comparison between these two things because I think in general that gadget isn't going to be sort of an algebra and might just be some sort of like module spectrum of some kind over maybe like or I'm actually not sure, but
yeah, no, like I said, I don't know. But it's a question I'd like to certainly think about more in the future. Cool. So remember, the whole point of this completion was to essentially, hopefully, provide a localization. These are the two things we would want. And again, it's not tremendously difficult to check that we have this first one. The second one, again, will often exceed what we were looking for and will have a weak equivalence. And when exactly that happens is where we're headed. It was a puppy break, so there has to be a corresponding kitty break. This is Smokey, and also another opportunity for any questions.
Okay, so I just wanted to ask, is T1 of T1 of A1 the associative operand?
I think no, because the associative operand, you've got to have like a sigma n somehow in there to cancel out, not just a point. So like the associative operand in spaces is like at level n, it's like sigma n embedded in spaces.
Yeah.
So I would think no.
Okay.
So this,
Yeah.
it looks like this story is about, as Liam asked, about Postnikov towers. But can you do sort of like a Whitehead story? Like if you instead of taking, I mean, as I call them sort of quotients, could you take like sort of sub-operads where you sort of kill off the first n, I don't know, arity operations?
Yeah. Again, unfortunately, the answer is I'm not sure. My concern is whether or not that would be an operad, whether or not you'd actually have those maps.
But I mean, you'd have maps from like into O, right?
I mean, if I take O and I kill off the first n terms, my worry is that won't be an operad. I'm not sure, but
it's going to be an operad.
Again, that's just I have like a little bit of a I'm not sure, but again, it very well could be, but yeah, I don't know.
Okay, that's fine. Thanks.
Niko, I have a quick question, just a general thing. Is there, I mean, sort of the topological under-equivalent homology that you referred to before has links to like deformation theory and obstruction theory. Are there some like naturally defined obstruction groups, or is there obstruction elements that appear in this context as well?
Yeah, again, that's like something I hope to look into. I don't know at this point.
That's cool. I was just getting excited about it all.
Yeah, cool. That's great. Yeah, these are all great questions. Just wish I had more answers for everyone, but yeah. Okay. So just a quick recap. I think just good to recap. This is the big analogy to keep in mind. We started wanting the part of a space that homology sees. I started with this adjunction, built this cosimplicial thing. We have that first property. The second property, we're not sure. So the sort of question that we're headed towards is, well, what about this comparison map? What can I say about it? Is it a homology iso? Is it weak equivalence? And then, of course, the same thing for O algebras, right? Wanted the part of an O algebra, the TQCs, start with this adjunction, build this cosimplicial thing, have first property, and now we want to ask about the second thing. Is it a TQ iso? Is it a weak equivalence? What can we say? So that's where we're headed. The cool thing is that there's often a weak equivalence between these. And that's surprising, at least to me, because this thing, right, is just built out of iterates of these guys, and they only see the homology of X. But somehow I combine them all in the right way, and I recover X, not up just to homology, but up to weak equivalence, up to homotopy. And similarly for TQ, out of these much, much simpler things, if I glue them together correctly, I recover A up to weak equivalence. So what we know is as follows. Bausfield and Kahn show that if a space is one connected, then it is Z-complete. That is, the comparison map is a weak equivalence. And the analogous result is from Xing Harper in 2019, which is that if an O algebra is zero connected, then it's TQ complete. And there is this dimension shift. The reason I'm claiming they're analogous is both that they can be proven in very similar ways, and also in a lot of ways, an O algebra being zero connected acts sort of similarly to a space being one connected. But actually more is true. What Bowsley and Kahn actually show is that a space is complete, Z-complete, if and only if it's nilpotent. So one connected spaces are nilpotent, but not necessarily the other way around. And that suggests that something should be going here, that there should be some improvement of Ching and Harper's results. And the direction that I'm really going to focus on is just nilpotent implies complete. That one. So if we're aiming to sort of fill this in, it's not a bad idea to start with, well, how do Bousfield and Kahn show this? How do they show that nilpotent implies complete? The key technical maneuver, the heart of their argument, is to understand what completion does to certain fibration sequences. Which ones are the principal fibration sequences? So we say that a fibration is principal if E to B fits into another sequence. So essentially, I mean, well, not essentially, just what it means is this fiber sequence can be extended to the right. And EBB prime is a fiber sequence, and FEB is also a fiber sequence. What they show is that Z completion preserves these sequences. So if you hand me FEB, that's actually a principal fibration sequence. There should be a principal here. Sorry about that. That's a principal fibration sequence. Then so is it still is after completion. How they then get the result is essentially saying that a space is nilpotent if and only if its Postnikov tower is actually built from principal fibrations, and then they just do an induction up the tower. That part's not too crazy. This is the real heart of what they do. So again, this is their theorem. I apologize again. There should be a big principal here. Principal fibration sequence. This is not easy to prove. Oh, sorry, the writing goes away apparently. The principal fibration sequence. In fact, it takes a whole section in their book, and I think it's worth pointing out why it's difficult. If we're trying to analyze this thing, well, how do we build B, right? It came from this cosimplicial thing. How did I build E? Came from this cosimplicial thing, F, cosimplicial thing. And I had these maps going down. We started with the fibration sequence, right? F to E to B, that's fiber sequence, life is good. But if you look at this next column, what I've done is taken a fiber sequence and applied Z tilde. And this is bad, and there's a couple of different ways to see it. First off, I've taken a fiber sequence, which is a limit, and I've hit it with a left adjoint, right? And generally speaking, left adjoints don't play well with limits. And the other way to see that this is going to be problematic is that essentially I've applied homology to a fiber sequence, and that doesn't usually work out nicely. That's kind of what the Serre spectral sequence or Eilenberg-Moore spectral sequence does for you. So maybe you could get a handle on this first column, even though it's not a fiber sequence. But the second one is also not a fiber sequence. The third one is also not a fiber sequence. So life's not great. And that kind of makes it surprising that this works out, because each level, none of the levels are fiber sequences, but somehow when you glue it all together, you do get a fiber sequence. So our motivating question is, well, what can I say about TQ completion? What does it do to fiber sequences, fibration sequences? Or even as a warm-up, are there O algebras that are not zero connected, but that are TQ complete? And it's worth pointing out that Bousfield and Kahn's proof really relies on one way of characterizing principal fibrations as coming from free group actions. And that just doesn't really make sense in our context. So their proof does not work in O algebras. So we don't have a complete answer, but what we do have is the following. If you hand me a fiber sequence in O algebras where the total and base O algebras are zero connected, then I still have a fiber sequence after completion.
Principal or not?
Sorry?
Should these be principal type of things, or?
Nope, this is just any fiber sequence where the base and total are zero connected. So it's not quite the exact analogy that we're hoping for, but this is sort of how we got to this result. And the strategy is basically going to be to show that F, its completion is a weak equivalence. And if these are 0 connected, F is necessarily only -1 connected. So we at least have a positive answer to this question. There are some, and sort of a partial answer to this. We don't have a complete characterization, but we have something. So let's see, we got, oh, perfect. So I just want to outline sort of the strategy of how to prove this. I'm going to skip the super technical details. But again, so we're going to consider sort of the most natural diagram. These right-hand arrows are weak equivalences because E and B are 0 connected. So that was already known. What we don't know about is this guy. And the strategy is to just show that that's a weak equivalence. If it is, then this lower sequence is weakly equivalent to a fiber sequence, and life is good. So the new goal is just to show that we have a weak equivalence here. And how are we going to do that? Well, first, let's consider how I built these things. Same way, right? B, resolution, B, resolution, and F into its resolution, and then maps going down. Just like in Bausfield and Kahn's case, we start off with a fiber sequence. Everything's nice. But right away, things go wrong. That's not a fiber sequence, that's not a fiber sequence, and that's not a fiber sequence. So we got to do something. And the problem we're facing is I don't really have control over this diagram, right? It runs away from me sort of at the first possible point that it could. So what we're going to do to at least maintain this control is, instead of looking at that, let me just, whatever the homotopy fiber of this map is, I'll just stick that here. Okay, so let's call that F0 tilde. Okay, so F0 tilde is just the ho5 of this map here. And same thing here. So forget this for a minute. Whatever the homotopy fiber of this is, stick that here. And same thing here. What this gets us is the following diagram. So this is just the last diagram, but now I've actually typed it. So here's what we got. Good news. Oh, so important to note, every column, right, is a homotopy fiber sequence. And the good news is that I have control over the diagram, right? I know that each column is a fibration sequence, so I know I'll have a fiber sequence after I apply Holim. But of course, the problem is that the very thing that constructed what we were interested in, right? We were interested in the map F to FTQ. That's gone, right? I kind of crossed that out. So somehow we need to get the completion of F back into the picture. So what we're going to do is take this top row, stick it down at the bottom, and, well, I wanted to get the completion of F into the picture, so let's just do that, right? I can just build up the cosimplicial diagram from F. That's ultimately what I'm interested in. And then, okay, I could do the same thing for each term in this row, right? I could complete, I could complete F0 tilde. Okay, I could complete F1 tilde. I could complete F2 tilde. And then I would have maps going to the right. So now at least I've got what I was looking for, right? I've got this left-hand column. And the idea now is to consider these maps first. We argue that these induce a weak equivalence on homotopy limits after I apply delta. We then consider these horizontal maps and argue that those induce weak equivalences on Holim delta. And by basically like a 2 out of 3, we can conclude that that map there in red is also a weak equivalence on Holim delta. So I've sort of fattened things up and broken this one problem into a bunch of smaller ones. And the upshot of this is that F into this Holim is a weak equivalence, but that's exactly the completion. So that, that finishes the proof. We're actually able to show something a little bit stronger, which is that if I look at this map of towers, so here I'm considering this as a constant tower. And then I look at the tower of truncated holoms. So if you're not familiar with this notation, this is basically just the tote tower associated to the cosimplicial diagram. That this is a pro-isomorphism for each star. So that's a bit stronger than just saying, well, after I take holom, I get a weak equivalence. It's also worth mentioning the same method of proof, but with a bit more analysis, proves the following generalization, which is that if I have a pullback diagram where B, X, and Y are zero connected, then that pullback diagram is preserved by TQ completion. And the same strategy is to show that A into its completion is a weak equivalence. And to get the original theorem, all you had to do is take B to be a point, and you get the fiber theorem. So this was, I think, supposed to be 50 minutes, so I will end it there. Thank you.
Thanks, Nico. On behalf of everyone, I'd like to thank Nico. If we want to all clap, we can. Is that a thing we want to do in GROOT? Yes? All right,
Yay.
we can clap. All right, so first section of questions will be recorded. So if you have questions that you'd like to also be included in the recording, you can ask them now. And then if those peter out, I'll turn off the recording and any other questions can be asked.
Nico.
Yeah.
So when you're talking about truncating operads, is it the case that if you take like the operad that its algebras are infinite loop spaces, is there one such that the truncations are like n-fold loop spaces?
That's a good question. So let's think. So the operad that gives you infinite loop spaces is the little disks operad. And the little n disks. I think so.
Okay, because
but I'm not sure.
I'm like motivated by the question I've always had, which is like if we have a space and all you know is that like for any n there's some space such that n-fold loops is equivalent to it. I always wondered, does that imply that it's an infinite loop space? And you afterwards you mentioned that you can like kind of you can like build up a tower and stuff using those things, and I'm wondering if that gives like an affirmative answer to this.
So you're asking like if I have a space X and I know there's some space A such that that's true.
Yeah, and A depends on n.
Okay, and that's true for each n.
Yeah, does that imply that X is an infinite loop space? And I imagine that would be the way to prove it if it's true.
Yeah. I would suspect no, because the space is changing each time. But I'm not sure. I am a little suspicious since this is changing every time, but I don't know.
Okay. Thank you.
Yeah.
Nico, I have a question.
Yeah.
So for your result, you're looking at tau 1 of your operad. Is there anything that you hope to be true for like tau 2 or anything else?
Yeah, I think that's like definitely, that's like been on the big to-do list. Because yeah, anytime you have an augmented functor, you can define a kind of completion. So you could certainly take X into tau 2 O of X and then 2 maps up. Whether or not, I mean, you think you have a map down, but even if not, all you really need is an augmented functor. And you get like a restricted cosimplicial space, but that's good enough to talk about completions. And what happens with that, I'm not sure. That's a really interesting question. And it's got to be related to Goodwillie calculus, because that tau tower is exactly the Taylor tower of the identity. So you're essentially talking about like completing with respect to layers of the, or not layers, but the parts of the Goodwillie tower. So I think that's really an interesting question, but I don't know at this point. The nice thing about tau 1 is it's basically stabilization. You're factoring through stable category, right? The first part, the first approximation, the Taylor tower is always stabilization. And the proof definitely uses that. It uses that I'm landing in a stable category before I come back. So I don't think the same thing would work for those higher guys, but I'm not, certainly an interesting avenue.
If you allow me to chime in on that point.
Yeah.
The tau 1 is going to give you stabilization. I just believe this has to be true. I don't know if it's actually like a fact, like if it's proved anywhere or not, but Hoots defines like n excisive approximations to a category. And I want to say almost certainly that these like tau 2 circle over O algebra, like tau 2 algebras have to sort of be or be very closely related to these like 2 excisive approximations to algo, and then as you go up the tower, similarly as well. You also have to be a little careful because you now are allowing for negative homotopy groups. So really most of these statements like allow to like really make sense for 0 connected guys and then probably like bounded below guys. But that's
there's always that question of convergence, I would imagine.
Yeah, because you're looking at the Bassfield-Kahn spectral sequence and things can start to go wrong.
Yeah. Well, so the nice thing about that is since we're stable, it's at least not fringed, but it certainly doesn't always converge. It certainly doesn't always converge. So yeah.
So can you maybe say a word about how you go about sort of executing the proof that the sort of desired arrows in that big bicosimplicial thing are equivalences? Is there some sort of like cubical analysis, like connectivity estimate type arguments that are going on? Okay.
Yeah. Thank you for asking. So these guys are a little bit easier. These are sort of formal. So how are these weak equivalences? So if you remember, F0 tilde was defined as the HO5 UQE UQB. U is actually a right Quillen functor, so that pulls out of the HO5. In other words, it commutes with that homotopy limit. And let me just call this UG. So when you look at this resolution here, there's going to be an extra codegeneracy, which is to say that what I'm looking at is like UQ, UG. Right, I always have 2 up, 1 down. UQ squared UG, 3 up, 2 down. And because of this, it's of this form, I can apply the co-unit here. I get an extra map down, an extra map down, extra map down. So that takes care of those guys. You're absolutely right about the horizontal ones. What you can actually show based on Ching-Harper's result is that you have increasing connectivity as you go up that Ho-Lim tower here. And then so in other words, F to the tower, the Ho-Lim delta less than less, F tilde. That's increasing in connectivity. And then by looking at certain cubical diagrams associated to homotopy limits of this shape, you can prove that the same is then true if I apply TQ homology. So Ho-Lim UQ F tilde. And then you just repeat this. So this is increasing in connectivity. That's increasing in connectivity, and so on. Does that answer your question?
Yeah, I think so. This is just kind of reminiscent of this recent paper of I think Dundas and Rogness on like cosimplicial and cubical descent, where they sort of do descent for some trace methods type gadgets on one connected maps.
Yeah,
But,
cubicle.
yeah,
Yeah,
right.
cubicle diagrams are like super useful, especially
Yes,
when you're looking
yeah.
at these truncated holons. So yeah, certainly.
Absolutely.
Yeah.
Yeah. Thank you.
Oh, yeah.
Any other questions for Niko? Okay, let's go ahead and thank Niko one more time.